Hi, ideal gas law. Nice. Now I've picked some examples that I'm hoping aren't super traditional so that you'll have some help and examples for the harder problems on your homework. So again, here's the steps that we follow. Once you read everything, label. That's always where you go so that you can identify where you are, where you want to end, what's the answer that they want, and then you can find the path in between. Next, identify the formula, solve for the unknown, so much easier to do that, and then plug your values in, put it in the calculator, do your plug and chug. Now, an important thing with the ideal gas law, anytime you see mass or moles, particles, so amount of substance, this is where you live, the ideal gas law. So if you see amount of substance, mass, moles, particles, you're going to have to use the ideal gas law because it's the only law that we have that relates amount of substance to pressure, temperature, and volume. Okay, so here's number one, size of container to hold of 0.459 moles. Oh, so right there I see moles, I'm starting thinking, okay, I probably have to use the ideal gas law. Of nitrogen at STP, and sometimes you'll get this at STP. So remember, STP, temperature, is 0 degrees C, and we always have to have temperature in Kelvin. So let's go ahead and add that 273.15 equals 273.15 Kelvin. Pressure, our standard conditions for pressure for gases is 1 atm. And then they give us moles. Remember N. N is our symbol for moles, and that is going to be 0.0459 mole. And what do they want? Size. So they want the volume. Okay, so I'm looking at this and I go, I see amount of substance, and we must use the ideal gas law. Well, the ideal gas law, remember, we always have R. You know, if you're ever wondering in life, do I know anything? Say yes, I know R. I know the gas constant, but 0.0821 atm times liter divided by mole times Kelvin. It could be a bumper sticker. I know something. I know the gas constant. Okay, let's go ahead and write down our formula. PV equals nRT. And I want to get V by itself. So let's divide both sides by P. We get V equals nRT divided by P. Now let's go ahead and plug in. We're going to do the plug and chug. So moles, let's see, we had 0.0459 mole times R. Actually, do you know what? I'm going to pull this down here because I want you to see the units very, very explicitly. V equals 0.0459 moles times the gas constant, 0.0821 atm times liter divided by mole times Kelvin times temperature, which was 273.15 K, divided by, wow, the pressure, which was 1 atm. Okay. So atm will cancel, mole cancels, Kelvin cancels, and check it out. We are left with liter, and that's what we wanted. Volume equals, and let's see what our value is. It is 1.03 liters, and there you have it. Now, some of you may have noticed something. There was another way that we could do this. I wanted to show you this way because I'd say 90% of students, this is what they'll do. They will do the ideal gas law. They'll see temperature, pressure, moles, and go, oh, great, ideal gas law. There is another way to do this, and it comes from Avogadro's hypothesis. Notice the key, we are at STP. There's a relationship, remember, between moles and volume at STP. Any gas, 1 mole of any gas takes up a volume of 22.4 liters. So we could have done, and you're going to look at this and go, man, that was easy. We could have done 0.0459 moles, 1 mole at STP, any gas at STP is going to take up a volume of 22.4 liters. And guess what? Moles cancel. When you multiply that, same answer, 1.03. So I wanted to show you this. When you're at STP, and there's a question between moles and volume, you can use a shortcut. Now, if you If that is like hard to remember in your brain, just do the ideal gas law. And like I said, most students do. But for those of you who picked that up, I wanted to show you there was a second way to do that, and it's totally fine, totally fine. And where this comes from, let me show you really quick. So at STP, you've got that pressure, the 1 ATM, the volume was our unknown, N, that was this value right here. R is always a 0.08 to 1. And then we've got the temperature, the 273.15. If we take these numbers and if we put 1 mole in right there, divide this over, you get that 22.4 when you solve for V. So that's why we can use that. That's why we can use that. They just did the ideal gas law for us, is really what it is. They did the ideal gas law for us. Okay, nice. Let's go ahead and work on the second one now. Okay, so again, I tried to pick a little bit harder questions to help you because I know you can do the easy questions. It's when you start getting harder questions, you're like, I don't know, there's not an example in the book for a hard one. Here we go. It says the mass of hydrogen. We want to know what is the mass. So what is the mass of hydrogen if the volume of this gas is 0.044 liters at 25 degrees C and a pressure of 3.81 ATM. Okay, it's asking for mass, grams, and you're thinking, I don't have any formulas that have grams. That's okay. You have moles. This ideal gas law, PV equals nRT, you've got moles and the gas. How can I go from moles to grams? Molar mass, periodic table. So you could be asked for mass, fine. You could be asked for particles, then you'd use Avogadro's number. Anything with amount of substance and you're dealing with gases, this is where your brain goes, is the ideal gas law. So can I find mass? Yes, but first we're going to have to find moles. So let's go ahead and label everything. First thing we always do, the pressure is 3.81 ATM, temperature 25 degrees C. Of course, we've got to bring that to Kelvin, so we do plus 273.15 equals 298.15 Kelvin. Our volume is 0.044 liters. We want mass, but to do that, I know we're going to have to find moles. So seeing amount of substance, I go, oh, we're using the ideal gas law. So let's go ahead and put R here, 0.0821 ATM times liter divided by mole times Kelvin. Okay, let's go ahead and solve for N. PV equals nRT. Divide both sides by RT. And we are going to get N equals PV over RT. Nice. Okay, last step. This is the fun one, plug and chug. So our pressure is 3.81 ATM times the volume was 0.044 liters. Nice. Now divided by R, 0.0821 ATM times liter divided by mole times Kelvin times temperature. Wow. Which was 298.15 Kelvin. Okay, let's look at our units. So ATM cancels, liter cancels, Kelvin cancels. And remember, when you have a fraction divided by a fraction, this mole, the fraction is going to reciprocate and multiply, so the mole comes up top in the numerator. So we'll end with moles. When you put all this into your calculator, and be careful, put that in parentheses, put that denominator in parentheses when you multiply it, we are going to get 6.9 times 10 to the minus 3 moles. Now this is moles of hydrogen gas, and they asked for grams. So this is H2. Let's go ahead and do molar mass to convert from moles to grams. 1 mole of H2 gas is 2.02 grams of H2. Remember, hydrogen is 1.01. Just multiply that by 2 since we have 2 atoms. And when we do this math, we are going to come up with 0.014 grams of hydrogen gas. Cool. So that's how we get the grams. Use the ideal gas law to find moles, and then just do molar mass to go one more step to get the grams. Nice. Now, these units may have been confusing for you. I want to break out the units and look just at those for a second. Let's just do the units on this problem. You have ATM times liter divided by ATM times liter divided by mole times Kelvin times Kelvin. Let's do just this part. I want to make sure that you can see how to do these units. Okay, so I can see that the Kelvin and Kelvin will cancel. Great. Now I have a fraction divided by a fraction. So again, you take the bottom fraction, reciprocate it, and multiply. So this is going to change to ATM times liter. And you take this, reciprocate it, and multiply times mole divided by ATM times liter. And now you can clearly see how ATM and liter cancel, and you end up with mole, and that's what we wanted. So there you have it. If you ever need to just do the units, take the time just to do the units. Make sure, because the units will always tell you if you're doing the problem correctly. Okay, last problem. This problem, more than any other, is what will stump my students, and they go, what? How do I do that? So question number 3, it says, what is the molar mass? What is the molar mass of 3.07 gram sample of some gas if the vessel is 3 liters at 300 Kelvin and 1.5 ATM? So they want molar mass. I'm going to write this down. They want a capital M. That's our unknown. And I'm going to put down the unit. The unit for molar mass, remember, is grams per mole. Okay, grams per mole. Well, check it out. They gave us the grams. Let me write that down. They gave us mass is 3.07 grams. Let's label everything else that they gave us. We have a volume of 3.0 liters, a temperature of 300 Kelvin, and a pressure of 1.5 ATM. Okay, great. I have everything labeled, but I'm still kind of chewing on this. How can I get molar mass? Well, again, I have grams. Now I see it. If I can find the moles, all I have to do is take grams, 3.07 grams, divided by the number of moles, and that will give me gram per mole molar mass. So I need to find moles. You know exactly how we're going to do this. Ideal gas law. So if you're asked for the molar mass of a compound, especially with gases, I want you to get used to this method. Write out the unit. Okay, molar mass, grams per mole, and then see what they gave you. Well, in this case, we got the grams. All we have to do now is find moles. And this is a common question with the ideal gas law. You have to find the moles, and then you can just plug it into gram divided by mole. Done. Nice. Okay, so ideal gas law, let's add the gas constant to it. R is 0.0821 ATM times liter divided by mole times Kelvin. Let's go ahead and solve for N. PV equals nRT, divide both sides by RT, and we get N equals PV over RT. So I'm going to come over here to plug these in. N is going to equal pressure, there it is, 1.5 ATM times the volume, 3 liters, divided by R, 0.0821 ATM times liter divided by mole times Kelvin times our temperature, which was 300 K. Let's look at the units, be sure everything cancels correctly. ATM cancels, liter cancels, Kelvin cancels, and there it is. We're going to be left with moles. So put this in our calculator, 1.5 times 3 divided by parenthesis, 0.0821 times 300 and parenthesis, and our answer is 0.18 moles. 0.18 moles. Okay, we got the moles. So let's come back up here for molar mass. They gave us the grams, 3.07 divided by 0.18 moles, and when you divide that, we get 17.06. So it'd be 17 grams per mole. Looks like it's ammonia. Looks like that is going to be pretty close to an ammonia gas. Okay, very good. hope that's helpful. Looking at some different angles, how we can use the ideal gas law. There's always the really, really obvious. You're given everything and you just find one unknown. They give you volume, moles, temperature, find pressure, great. They give you grams, volume, temperature, you find pressure. If they give you grams, use molar mass to go to moles, and then you can plug it in. These are kind of the unusual ones. If you're using STP, you can still use ideal gas law. If you want mass, remember, or particles, find moles, then you just walk the bridge to go to grams or particles. And then molar mass, all you have to remember is the grams per mole on that. The key to any of this, labeling. Label everything. Label what they give you, label what they want, and then you can work it, you can fight your way through it and figure it out. So good job. Have fun with the ideal gas law.